Greetings, Dr. Sharma. Greetings, my fellow colleagues. Today, I will take you through our supervised machine learning term project, which we tackled this semester in our ISM course. And the question that I decided to partake or to take over was, how do real life statistics of NBA players influence their video game ratings, right? And for some context, these ratings generally go from 0 to 99. We see LeBron James in this picture here, which is one of the best players in the NBA. And so rightfully, he has a really high overall rating of 97 in the 2023 version of the game. But we'll look at some statistics from the 2019 to 2020 season and see how that influences the 2021 video game ratings, right? So without further ado, let's get into the purpose and problem of this data mining task. So I don't know about you guys, but I'm an avid sports fan, an avid video game fan, and every year when NBA 2K releases, I am thrilled to see what players' ratings went up, what players' ratings went down. And so the problem, given that we're going to tackle in this project is, can we predict NBA 2K player ratings based on their real life statistics, right? And like I mentioned earlier, we're going to take the 2019 and 2020 NBA stats from that season and see what the influences are on the NBA 2K21 video game ratings. That's how the ratings are produced. They're produced from the previous season. And ultimately, the purpose is to accurately predict these player ratings based on those stats, right? So we'll take a chunk of new data from the existing data set that we're going to have and see how our model is able to match up prediction-wise to the actual statistics. And so we'll get to that a little bit later in the presentation. But ultimately, we want to accurately guess these ratings, and perhaps we'll be able to figure out a lever to guess future ratings of future versions of the video game. Now, as we get into the data cleanup process, it's important to note that the original data set had a ton of predictor variables, but I was able to shave off some of the variables such as field goals attempted and made, three-pointers attempted and made, free throws attempted and made. And the reason I did this was because we already had field goal percentages, three-point percentages, free throw percentages that already essentially embedded the percentages of attempted versus made. And so that was a little bit redundant. So I decided to shave that off. Also, individual offensive and individual defensive rebounds were independent stat categories when we already had total rebounds or average rebounds for that player for the given season. And so I decided to shave off the individual rebound categories as well, just to have one rebound category, again, to eliminate some of that redundancy. And then some of the other statistics or predictor variables that we received, such as points for, FP, DD2, TD3, plus or minus, games played, wins, losses, and minutes played, those were more team oriented and based on coaching decisions. They weren't really player statistics or influential in the player's performance, so to speak, that would then influence their player ratings. And so I shaved that off as well. I reduced those dimensions. And then essentially, another important note is that for both algorithms, for the linear regression and for the KNN, I decided to take two different chunks of 50 essentially sets of the data for the later predictions, right, to match up against, just to really challenge the algorithm and see if I could get really good results despite taking different sections of the data for essentially for scoring, right? And then as we did the missing data handling, as we can see here in the screenshots, I decided to do mean treatments for the continuous data, which was pretty much all of it, and then really the delete record for other parts of the data, which was just text. And I got 0 treated records across both times that I did it for the different algorithms, and so the data was ready to go after this. Now, as we got into the data exploration and the scatter plot matrices, I was able to figure out that really field goal percentage, 3-point percentage, and free throw percentage had a really heavy correlation with average points, and rightfully so, right? How else do you score points if it's not through field goals, 3-pointers, and free throws in basketball? And so those had a really high correlation, and you can see in the scatter plot, there's sort of these jumbled plots just straight up or straight to the side. And so I decided to reduce those dimensions and really leave it to average points, which I felt encapsulated all those different percentages for those players and their effectiveness in scoring points. And so after shaving off those dimensions, I was left with 7 predictor variables newly, right? And then the other scatter plot to the right, we can see there's sort of a correlation between age, the player's age, and the average points they're able to score, right? And I thought it was really cool because we can see through these scatter plots that the really young players, the rookies, they tend to score less points. The older players, the grizzled vets, also tend to score less points. And then we see the sort of players that are in their prime of their career, sort of that middle age, right? From like 23 to 28 to 31, so to speak. Those are the players that tend to score the most points. And it sort of serves to prove that phenomena of career prime, as they say in sports. And that's why I decided to include it. I thought it was an interesting caveat as it pertains to our project. And then also important, I didn't have to do any encoding because there was no categorical variables. All of my predictor variables were continuous data, continuous numerical data. Okay, now really quickly, the technique or algorithm that I decided to use were for one, linear regression, which is ideal for use on continuous numerical data. And well, I'm working with statistics, I'm working with overall ratings, all continuous numerical data. And so linear regression was a no-brainer, right? And then K nearest neighbors or KNN is also useful for both continuous numerical data, which is the sort of data that is a priority for me or was a priority for me in this project. And then it also is useful, interestingly, for categorical data, which we didn't necessarily need for this data set, but it's another caveat there for KNN or in favor of KNN. And really, the reason I chose these two different techniques or algorithms was because throughout the semester, those were the ones that I developed the most comfortability with. I felt familiar with them, I knew how to navigate them, and I understood them pretty thoroughly. And so I decided to tackle this data set with those two algorithms. Now, as we get into model construction, I think it's important to highlight the partitioning that I decided to use. And so for the linear regression algorithm, I decided to use partitionings of 60-40, 70-30, 80-20, 90-10, 55-45, which was the partitioning that I used when I did the PCA analysis of the top five for a specific model. And then the sixth model was 75-25. For the KNN algorithm, I decided to do 65-35, which was, again, the PCA analysis for that specific model, again, for the top five. And then I again did 75-25, I did 85-15, I did 55-45, 90-10, and 60-40. And then specifically the KNN, the neighbors that I used in that corresponding order was 3 neighbors, 4 neighbors, 2 neighbors, 4 neighbors, 5 neighbors, and 5 neighbors again. As it pertains to the principal component analysis, the PCA, I did top 5 for both models for one of the 6 models in both of the algorithms. And interestingly, both of those models, when I did the PCA component analysis, the top 5 components or the top 5 predictive variables that it churned out was average turnovers, average blocks, average steals, average rebounds, and player age. And so I used those for the PCA top 5 model particular to each algorithm. And really each of the linear regression and KNN algorithms, as I mentioned earlier, had different sets of data to process, right? Because I took 2 different chunks of new data to score. For the linear regression, I took 50 of the data plots from the bottom of the data set, and then for the KNN, I took 50 of the data plots from the top of the data set. And so both algorithms dealt with stored a slightly different set of data from the same data set, so to speak, if that makes sense. And the way that we decided which was the best model for scoring or for deployment was, again, highest validation R2. And we'll get to those best models a little bit later in the presentation. And overall, right, sort of some foreshadowing here, the linear regression models had the greater validation statistics across the board, as they all were at least or over 91%, with the exception of the PCA model, which was around 79%. Now, as we get into the model tables, right, particularly this one's for the linear regression algorithm that I used, and I deliberately put Michael Jordan aside of it because it was the strongest of the 2 models. But really the model that was the best performing for this algorithm was model 4, or linreg stored 3, which yielded a validation R2 of roughly 92%, slightly edging out all the other models that came in at around 91%. And interestingly, the PCA model, which is sort of a trend that we'll see here with this next model table as well, was the lowest performing model out of the six, coming in at just 79% validation R2. But ultimately, we used the LinReg stored 3, the 92% validation R2 for deployment. And here in this model table, we can see all the different dimension reductions, the different partitioning that we used, whether or not we did PCA, which we did for just one model, the different trainings, the validations, and the squared errors as well. And that's our model table for linear regression. Now, as we get into the model table for the KNN algorithm, an interesting caveat here to notice is that all of the training R2s for all of the models for the KNN delivered 100%. So I instantly got worried of some overfitting, some overconfidence, but then I was relieved to see some good validation R2s for the most part, right? Hovering around the 84% range. And then finally getting the strongest model, which was the last model, model 6, or KNNP stored 5, which gave us a validation R2 of 85%, right? Just slightly edging out all the other models. And eventually that would be the model that we would deploy for this KNN algorithm. And again, we can see the different dimension reductions, whether it was PCA or not, and then the squared errors for each model, the validation versus training R2s for each model as well here. And now we get to the moment of truth, right? The deployment, the scoring, the predictions, did the model work? And as it pertains to the algorithm for linear regression, or the linear regression algorithm, I should say, we again deployed the best model, LinReg stored 3, which was the fourth model out of the six, with a validation R2 of roughly 92%. And I was thrilled to see how incredibly accurate this model produced some of these predictions. And they're not all 100% exactly, right? We can see here in the screenshot that we have the predictions next to the real ratings given by the actual data set, just for comparison reasons. And they're not all exactly 100% matches, but there are some that are spot on. There are a lot that are spot on. And then the ones that are misses are just really slight misses, right? By 1 point or half a point, or whatever the case may be. But it's really slight misses. And so I was really encouraged to see that the model performed strongly in terms of linear regression, which I was sort of expecting, given that linear regression was the MVP of continuous numerical data machine learning, right? Now, as we get into the deployment for KNN, I'm still super enthusiastic about the predictions because they were reliably accurate. However, we can begin to see some of that drop off, right? And that is to be expected given the lower validation R2. And you can see the algorithm sort of got a little overconfident with that 100 training, but the validation R2 nonetheless still produced a strong model, right? Where we can see there's some 100% matches, not as much as the linear regression model produced. And there are some slight misses as well. Now, what we'll see with some of those slight misses, even though they're still, relatively slight, 1 point, 2 points, is that there will be some misses that have more of a range or more of a width apart than some of the misses that we experienced with a linear regression model. So KNN was a strong model. The KNNP stored 5 was a really strong model, given the 85% validation R2, but it did underperform relative to the linear regression model that we also yielded. And ultimately, to conclude, we can say that the linear regression model was stronger at predicting, right? If we take a closer look at those deployment prediction results, and really all the validation R2s for the linear regression model were greater, right? Not counting that PCA model, of course, but they were all greater than the validation R2s boasted by the KNN model, which were, again, all strong, given that they were higher than 77% validation. Again, not counting that PCA model and I say not counting that PCA model because both PCA models were the worst performing among the models for both algorithms, right? The PCA model for both algorithms really had the worst validation R2s. For linear regression, that was 0.798, and for KNN, that was 0.563, both all-time lows given relative to the 6 models that were conducted in each algorithm. And again, another caveat that we mentioned a little earlier was that the KNN models all had 100% training R2, perhaps signaling some overconfidence, which had me worried. But ultimately, the validation R2s were really strong, and so that gave me some relief for sure. And again, overall, the models were all really accurate, which I was pleased to see those results. And next time you want to know some ratings ahead of time for the next versions of NBA 2K, I might just have the cheat code for you. Now, very briefly, to touch upon the case studies that I researched for each algorithm, the first of those algorithms being linear regression. And the first case study, the first instance of the case study was that multiple linear regression was being used as it pertained to data mining in predicting Apple's stock price, right? And as a finance major or a previous finance major, that instantly grabbed my attention, right? To think that I can use data mining, which is a skill that I newly acquired thanks to this course, to perhaps give me an edge in the market. And we saw in the case study that multiple linear regression was effective in taking the historical stock prices and some other indicators to effectively predict what some of those future stock prices would look like, right? And then the second instance of a case study was for predicting rainfall, using multiple linear regression to predict rainfall, again, for agricultural purposes more particularly, and also for some safety purposes, right? The case study that I looked into was more pertaining to the North Himalaya region, where it was important to predict rainfall to know different agricultural seasons, different agricultural yields, and things of that sort, and also for some safety reasons for the citizens that populated that area. Okay, now in the penultimate slide of the presentation, I will touch upon the case studies that I found for K nearest neighbors, which was the second algorithm that I decided to use for this term project. Now, these two juxtaposing case studies, I think, really serve to showcase the capacity of KNN as an algorithm, right? And in the first case study, we saw KNN being used for customer segmentation. Particularly, IBM was using nearest neighbors in terms of purchasing data to be more effective in their target marketing for their computer sales for their customers. And then in the second case study that I researched, I was able to see KNN in a categorical data capacity, as KNN was being used to categorize various species of the iris flower given distinct characteristics, right? And in that case study, it turns out KNN was really effective at detailing what these various characteristics suggested that specific flower or what species that specific flower pertained to. And finally, here are my references. Here I include the reference for the data set that I used for the term project, the supervised machine learning. And then I also included the references for the various case studies that I just highlighted in the previous slides. If anybody is interested in taking a deeper look at that, I found it really interesting. And ultimately, I'd like to thank you all for listening. I'd like to thank you, Dr. Sharma, for all your time, effort, and consideration throughout the semester. I've thoroughly enjoyed this class. Thank you.